Hi everyone, today I'm going to present a thorough introduction about finite volume method. In this presentation, first I'm going to talk about the governing equations of fluid flows, including the conservative and non-conservative forms of the governing equations. After that, the finite volume method is presented in detail. Governing equations of fluid flows. The governing equations of fluid flows express mathematically the conservation of mass and momentum of a fluid flow. The fluid is regarded as a continuum. In other words, the fluid flow will be described using the macroscopic properties such as velocity, pressure, density, and temperature, and their space and time derivatives. Note that the governing equations of fluid dynamics are considered as the cornerstone of computational fluid dynamics. They are the mathematical statements of three fundamental physical principles upon which all of the fluid dynamics is based. 1. Mass is conserved. 2. F equals ma, Newton's second law. 3. Energy is conserved. The differential form of the unsteady three-dimensional mass conservation at a point in a compressible fluid in a Cartesian coordinate system can be written as shown here, where rho is the fluid density, u the velocity component in x direction, v the velocity component in y direction, and w the velocity component in z direction. Using the divergence operator, the continuity equation can be written in a more compact form as shown here, where u is the velocity vector. In these equations, the first term, which is called the transient term, indicates the rate of change of mass, and the second term, which is the convective term, shows the net flow of mass out of an infinitesimal element. For an incompressible fluid, the density is constant, and therefore the transient term becomes zero as shown here. The x component, y component, and z component of the momentum equation are presented here, where P is the pressure and tau ij is the viscous stress. Suffices I and j means that the stress component acts in the j direction on the surface normal to the I direction. In a Newtonian fluid, the viscous stresses are proportional to the rates of deformations as presented here, where mu is the dynamic viscosity and lambda is the second viscosity, which relates stresses to the volumetric deformation. Note that for an incompressible fluid, the dot product of nabla and velocity is zero. The second viscosity is normally approximated as shown here. Thus, substituting the above stresses into the momentum equations and rearranging the viscous stress terms yields the so-called Navier-Stokes equations. Conservative form of the governing equations of fluid flow. Mass equation, x momentum, y momentum, z momentum. As can be seen here in these equations, the conservative form of the governing equations contains terms which include the divergence of some quantity. For this reason, the conservative form of the governing equations is sometimes called the divergence form. Normally, in the finite volume method, we use the conservative form of the governing equations, which guarantees the conservation of the variables in each volume control and consequently in the whole computational domain. As can be seen, there are 4 equations and 5 unknowns, which are 3 components of velocity, a pressure, and rho density. The 5th equation is the equation of state. Therefore, this system of equations can be considered closed and it can be solved to obtain the unknown variables, provided that suitable auxiliary conditions, initial and boundary conditions are supplied. Generic form of transport equations. As can be inferred from the conservative form of the governing equations, the governing equations for a general scalar variable phi can be written as shown here. Here, phi is a general scalar variable. The first term is a transient term which shows the time rate of change of phi. The second term shows the rate of decrease of phi due to convection. The third term indicates the rate of increase of phi due to diffusion. And the last term is the source term, which shows the rate of generation or destruction of phi. The starting point for computational procedures in finite volume method, which will be presented later in this video, is this equation. Note that this equation turns into continuity and momentum governing equations by setting phi equal to 1, u, v, and w, and choosing proper values for the diffusion coefficient gamma. In the finite volume method, this transport equation will be integrated over each cell as shown here, where this sign is the volume of the control volumes as shown here. Using Gauss divergence theorem, the volume integrals of convective term, second term, and diffusive term, third term, as shown here, are transformed into integrals over the entire bounding surface of the control volume as shown here. The order of integration and differentiation of the first term can be changed to clarify its physical meaning. This first term shows the time rate of change of phi within the control volume. The second term is the rate of decrease of phi due to convection. The third term is the rate of increase of phi due to diffusion. And the last term is the source term. Mathematical classification of governing equations. The governing equations presented in this section can be used to solve two general class of fluid flow problems: A, steady state, B, transient. Steady state problems, which are also referred to as the equilibrium problems, are concerned with the calculation of the steady state distribution of variables, such as the steady state distribution of temperature in a rod of solid material. These problems are also called the boundary value problems, since the steady state distributions of variables depends only upon the values of the variables on the boundaries. The steady state problems mathematically are considered as elliptic types. The information about the solution travels equally in all directions. In these problems, the solution domains are usually closed, where boundary conditions are imposed over the domain's boundary. The transient problems, which are also referred to as the marching problems, are concerned with the unsteady, time-dependent flow phenomena. These problems are also called the initial boundary value problems. The transient problems mathematically are considered as hyperbolic and parabolic types. In the hyperbolic type, the information about the solution propagates in two sets of directions, while in the parabolic type, it propagates along a single direction. An example of hyperbolic type can be supersonic flows, such as shock waves, while the parabolic type can be subsonic flows, such as wakes. Finite volume method. The finite volume method is one of the most popular methods for the discretization of the governing equations in CFD community. The popularity of the finite volume method in CFD stems from the fact that it reflects the physics and the conservation principles of the fluid flows, such as the integral property of the governing equations. In this method, the computational domain is discretized into a finite number of control volumes over which the integral form of the governing equations is discretized. The discretized governing equations in the whole computational domain form a system of algebraic equations as shown here. Finally, this system of algebraic equations is solved to obtain the solutions. Basic methodology. The general workflow of the finite volume method is presented here for a CFD simulation of a horizontal axis wind turbine as an example. 1. The desired computational domain is precisely specified. 2. The computational domain under consideration is divided into computational grids using a finite number of control volumes or cells. 3. Integral equations are discretized over each of these control volumes. 4. Discretized equations that form a system of algebraic equations are solved. Control volumes, cells. The control volume cells can be structured or unstructured, Cartesian or non-Cartesian. For instance, this figure shows a three-dimensional control volume with a node in its center and adjacent nodes. Note that the values of the variables are stored in these nodes, which are usually placed in the center of the control volumes. Considering the center of the control volume P, adjacent nodes along the coordinate axis are generally named east, west, north, south, higher, and lower nodes and are capitalized. The lowercase letters represent the surfaces of the control volume. This figure shows a one-dimensional control volume where the eastern, western, and central nodes together with the eastern and western surfaces of the central control volume are shown. The area of the control volume surfaces is indicated by AW, AE, AN, AS, AH, and AL. In structured grids, we can use I, J, and K as underscripts to identify the nodes as shown here in this figure. Based on this figure, the nodes can be represented using two different methods. Accordingly, the value of phi at cell P on the right-hand side grid is equal to the value of phi at the cell IJ on the left-hand side grid. Additionally, for the values of phi at the northern, southern, western, and eastern cells, we have these relationships. Steady-state convection-diffusion problem. The steady-state transport equation of a variable phi is written as follows. The first term is the convective term and the second term is the diffusive term. So, as we are considering the one-dimensional case, we will use this one-dimensional uniform grid over which the steady-state transport equation for the variable phi is integrated. Here, uppercase W, P, and E indicate the centers of the western, central, and eastern control volumes respectively. The west side face of the central control volume is referred to by the lowercase w, and the east side face of the central control volume by the lowercase e. The distances between the nodes W and P and between the nodes P and E are identified by delta XW and delta XE respectively. Similarly, the distance between face W and face E is denoted by delta X. Steady-state one-dimensional pure diffusion problem. Now consider a steady-state one-dimensional case without the presence of a fluid flow, i.e. U equals 0. In this case, the transport equation is written as follows. This equation is integrated over the one-dimensional control volume as shown in this figure as follows. As a result, we will have the following equation. To discretize the diffusion flux, it is necessary to estimate the gradient of the variable phi over the control volume surfaces using the nodal values. The simplest estimate is to use the central differencing method as shown here for the gradient of phi at the eastern face of the central control volume. In other words, the central differencing method assumes that there is a linear function between nodes. Therefore, there are several important points to keep in mind here. 1. In the finite volume method, fluxes are needed at the control volume surfaces, not at the nodes. 2. The central differencing method that we use to calculate the gradient of phi at the faces of the control volume, as is based on a linear function, has the accuracy of second order. 3. In the central differencing method, equal effects are applied for nodes on both sides of the control volume surface because diffusion works equally in all directions. This action is not practical at all in the presence of convection. 4. A similar relationship should be written for the western surface. This is necessary in order to respect the principle of conservation. In other words, the output flux from a control volume, according to this figure, is equal to the input flux to the adjacent control volume. This property, where the principle of conservation is guaranteed in each volume control, is the main advantage of the finite volume method compared to the finite difference and finite element methods. So now let's continue the discretization process of the diffusion term. The gradient of the variable phi over the western surface of the control volume by the central differencing method is as follows. The diffusion coefficient D is commonly used in the discretized equations, which is defined as follows for the eastern surface as shown here. Therefore, using the diffusion coefficient, the gradient of the variable phi over the eastern face of the central control volume can be calculated as follows. Similar relationships can be written for other surfaces of control volume. Establishing a matrix equation. In the absence of a velocity field, i.e. u equals 0, the steady state diffusion problem is written as follows over the one-dimensional uniform grid presented in this figure. By estimating the gradients of the variable phi using the central differencing method, we will have this equation. The above equation can be rearranged as shown here. This is the discretized equation of diffusion flux and can be rewritten in the following standard form, or in a more compact form as shown here. Here NB stands for the neighboring cells. This equation is the standard form of the discretized transport equation for the general variable phi. The same standard form is applied to 2 and 3-dimensional problems. This equation is the discretized transport equation for a single control volume. If we apply this equation to all the control volumes, we are going to have a series of algebraic equations as shown here. This equation can be easily solved by calculating the inverse of this matrix. However, for two reasons, such a method is not generally used in CFD. One, in larger and more complex problems, the number of nodes can be more than 1 million. Thus, the size of the resulting matrix can be more than 10 to the power of 6 times 10 to the power of 6. The computer memory required to store the information of this matrix is 4 times 10 to the power of 12 bytes, or 4000 gigabytes, which is more than the capacity of existing supercomputers. 2. Navier-Stokes equations that govern fluid dynamics are nonlinear equations, and to solve these equations numerically, it is necessary to use iterative methods. Therefore, instead of using the inverse of the matrix, different iterative methods are used to solve the discretized equations. Steady-state two-dimensional pure diffusion problem. The two-dimensional steady-state diffusion problem is described using this transport equation, where F, which stands for flux, and nabla are defined here. The two-dimensional Cartesian grid, which is used for the discretization of the stated two-dimensional diffusion problem, is shown here in this figure. Again, here our focus will be concentrated on the cell P and its neighboring control volume. Based on this figure, the volume of a cell is calculated using the following equation. This equation will be integrated over the cell P as shown here. Using Gauss divergence theorem, the volume integrals are transformed into integrals over the entire bounding surface of the control volume as shown here. Based on this figure, this integral equation can be written as follows. This equation, according to this figure, indicates the balance between the fluxes in the control volume. As the areas of the control volume shown in this figure are as follows. Therefore, the flux is shown in this figure, and this equation can be calculated as follows. Assuming that the variable phi changes linearly across the control volume surfaces, the gradients presented in this equation can be estimated again by using the central differencing method. Therefore, the input and output fluxes to the control volume in terms of the nodal values are written as follows. Note that we can simplify the source term by defining this term as a linear function of the value of the variable phi at cell P as shown here. Thus, the discretized form of the transport equation describing the two-dimensional steady-state diffusion problem is as follows, where the coefficients are presented as follows. The same method can also be used to obtain the discretized form of the transport equation describing the three-dimensional steady-state diffusion problem. Several important points about the discretized equations for steady-state diffusion problem are presented here. 1. The discretized equations represent the balance of fluxes and the source term. In this way, the principle of conservation in any control volume is guaranteed. However, total conservation in the whole computational domain is not achieved until the output flux from a control volume enters exactly the adjacent control volume as shown here. 2. Coefficients AP and ANB, which NB stands for the neighboring cells, as highlighted here, they should always have the same sign. Generally, they are always considered positive. 3. if the source term is equal to 0, S equals 0, then we will have this relation between the coefficients of the discretized equation. The standard discretized equations can be rewritten as follows. In this equation, we have this relation between the coefficients. Given that the value of the variable phi at P is the weight sum of the values of phi in the adjacent nodes, the value of phi P is bounded by the values of phi in the neighboring cells. In other words, the value of phi P is limited by the values of phi at the boundaries. More precisely, the value of phi P cannot be more than the maximum value or less than the minimum value of phi in the neighboring cells. However, if the source term is different from 0, the value of phi P is not necessarily as constrained as before and can take values higher and lower than the maximum and minimum values of phi in the neighboring cells. Discretization of the diffusive term over non-orthogonal unstructured grid. In uniform structured grids, as can be seen here, the fluxes are normal to the face. In these grids, as shown here, the gradient on the east face side is calculated as follows, where RE and RP are the position vectors of the centers of the control volumes P and E with respect to the X or Y coordinate system. However, most of the times the grid is unstructured, which results in non-orthogonal faces with respect to the vectors connecting the two cell centers as shown here. In non-orthogonal unstructured grids, the gradient direction that yields an expression involving phi P and phi E, the values of phi at the cell nodes P and E, will have to be along the line joining the 2 points as shown here. If the vector P as shown here represents the unit vector along the direction defined by the line connecting nodes P and E, then this unit vector can be defined as shown here. Thus, the gradient in the P direction can be written as follows. Thus, to achieve the linearization of the flux in non-orthogonal grids, the eastern surface vector SE as shown here should be written as the sum of two vectors HE and TE as presented here, with HE being in the PE direction to enable writing part of the diffusion flux as a function of the nodal values phi P and phi E, and SE is the eastern surface vector. Thus, this expression is obtained for the flux value at the eastern face side of the control volume P. The first term on the right hand side is similar to the expression obtained for the orthogonal grids involving the nodal values phi P and phi E, while the second term on the right hand side is called cross diffusion or non-orthogonal diffusion and is due to the non-orthogonality of the grid. Different options for the decomposition of SE are available, such as minimum correction approach, orthogonal correction approach, over-relaxed approach. However, the most stable convergence in the CFD solutions is achieved by using the over-relaxed approach. That is the main reason why the over-relaxed approach is the most preferred approach in the CFD community. Here, I'm going to briefly present this scheme. In this scheme, as shown in this figure, TE is selected to be orthogonal to SE. Thus, HE is computed using this equation. Here, we have multiplied both the numerator and denominator by the magnitude of the vector SE. Note that theta is the angle between the vectors SE and P, or between the vectors SE and HE. Therefore, for non-orthogonal grids, the diffusion flux at an element phase cannot be written solely in terms of the values at the nodes on two sides of the phase. A new term needs to be added that accounts for non-orthogonality. This term is denoted in the literature by cross diffusion. Steady-state convection-diffusion problem. In nature, diffusion is always accompanied by convection. The general form of the transport equation for the scalar variable phi in steady state is as follows. So far in this video, the discretization of the diffusion term was studied by the finite volume method, Here, we will focus our study on the convection term and its fundamental difference from the diffusion term in the context of the finite volume method and related problems. We will also develop a method for solving the convection-diffusion transport equation. As observed previously, the diffusion term was discretized using the central differencing method. Thus, it makes sense to use the same method for convection term. However, the diffusion process affects the distribution of a transport quantity along its gradients in all directions, while the effects of convection are only in the direction of flow. We assume that the fluid flow is known, and therefore we aim at determining the transport and distribution of the scalar quantity phi in this flow field. Steady state one-dimensional convection diffusion equation. The transport equation for the quantity phi over a one-dimensional flow field U, as shown here in this figure, is expressed by the following equation. This flow must also satisfy the continuity equation. This equation will be integrated over the control volume P presented in this figure, which yields this equation. In fact, this relationship from a physical point of view means source equals input flux to control volume minus output flux from control volume. Fluxes in this equation consist of convection and diffusion terms as shown here. Accordingly, this equation can be written as follows. And integrating the continuity equation over the control volume P yields this equation. Considering that the eastern surface area equals the western surface area equals A, as shown here, and the volume of the control volume P is estimated using this equation, and using the central differencing method to discretize the gradients of the diffusion terms, we will have this equation. Through defining the following parameters, C, convection transport coefficient, D, diffusion transport coefficient, this equation can be rewritten as follows. And the continuity equation is written as shown here. Since velocities are assumed to be known on control volume surfaces E and W, it is only necessary to calculate the transport quantity phi on the surfaces E and W as shown here. The method of specifying these phase values is denoted in the literature by the advection scheme. Different methods are presented for this purpose. Central differencing method. Now we need to estimate somehow the values of phi at the control volume surface E and W by using the values of phi stored in the nodes. One method that can be used for this purpose is the central differencing method, which was used for the discretization of the diffusion term in the pure diffusion problem. In this method, according to this figure, it is assumed that the variable phi changes linearly between the nodes. Therefore, based on this figure, the values of phi at the control volume surfaces E and W can be estimated as shown here. Substituting this equation into this equation, which is the discretized transport equation obtained earlier, yields this equation. This equation can be written as follows in the standard form. The coefficients of the discretized equation in the standard form are given here. In this regard, the mass conservation imposes the following constraint on the values of CE and CW. D, as we can see here, DE and DW is always positive, but C, CE and CW can be negative or positive depending on the direction of the flow. Therefore, considering that the coefficients of the discretized equations should always be positive to guarantee the stability, this relationship must be satisfied between D and C. In other words, the absolute value of C must be less than to D. To further explain this issue, we use the Pecklet number, which is defined as follows. This number, in fact, represents the ratio of the advective transport rate of phi to its diffusive transport rate. Now, let's consider the following two different conditions. In the first case, the convection effect is much less than the diffusion. In the second case, the effect of convection is much greater than the diffusion. For example, for the first case, consider that Pechle is equal to 0.5, while for the second case, Pechle equals 4. Now for Pechle equals 0.5 and 4, this equation is solved by assuming that there is no source term, i.e. S equals 0. And the distribution of phi is obtained and the results are compared against the exact solution as shown in the following figures. As can be inferred from these figures, while in the first case, which is equivalent with Pechle number equals 0.5, the results of the numerical solution are completely consistent with the results of the exact solution. In the second case, which is equivalent with Pechle number equals 4, the results are not consistent at all. This solution indicates that some of the assumptions used in the discretization of the equation are unrealistic or unphysical. Thus, the question that arises here is that what is the reason for this behavior? As observed previously, the coefficient at the eastern phase is defined as follows. There is a possibility for this coefficient to become negative, thus leading to unphysical results as shown here. This equation can be rewritten as shown here. Considering the definition of Pechle number, we're gonna have this equation. Thus, from a mathematical point of view, it can be argued that for Pechle numbers larger than 2, some of the coefficients of the discretized equations become negative, and this consequently eliminates the boundedness of phi p with respect to the adjacent nodes. But from a physical point of view, the problem can be traced to the performance of the convection term. As can be seen in these figures, the convection process, contrary to the diffusion process, is a directional vector process. In the convection process, the property phi is transported only in the direction of the flow, whereas the diffusion problems affects the distribution of the property phi along its gradients in all directions. That is why the central differencing scheme works very well for the pure diffusion problem, while it fails in the case of convection diffusion problem. The central differencing scheme is unable to account for the flow direction, and instead it considers that the fluid flow has the same effect on the upstream and downstream directions. Note that according to the definition of the Pechle number, this situation can be avoided by decreasing the grid size so that the Pechle number remains smaller than 2. For many practical situations, however, the increase in storage and computational requirements may be too large to afford. Moreover, for pure convective flows, this is simply not feasible. Therefore, a remedy is needed. Upwind scheme. One of the disadvantages of the central differencing method is its inability to determine the direction of the fluid flow. In this method, the amount of quantity phi at the eastern surface of the control volume is always affected equally by phi p and phi e. This method is unsuitable in the presence of severe west to east convection, as the western surface will have a larger effect on the value of phi at the east side surface than the eastern side surface. To calculate the value of phi at the surface of the control volume, the upwind scheme accounts for the flow direction and thus the transport of information from upstream. Therefore, based on these figures, if the velocity at the eastern phase E is greater than or less than 0, i.e. CE greater than or less than 0, the value of phi at the eastern phase is calculated as follows using the upwind scheme. This relationship actually implies that the value of phi on the eastern surface is determined only by the value of phi at upstream node in the flow direction. A similar equation can be obtained for all the surfaces of the control volume. Using the upwind scheme, the discretized convection-diffusion algebraic equation in standard form is written as follows. Using the upwind scheme to solve the problem solved earlier by the central differencing method, it can be observed that for Pechle number equals 0.5, the upwind scheme is not as accurate as the central differencing scheme. This is because the upwind scheme is first order accurate, while the central differencing is second order. For Pechle number equals 4, the solution obtained using the upwind scheme is not very accurate, but the oscillations in the results are disappeared. Therefore, the upwind scheme provides stability for simulation at the expense of reduced order of accuracy. Properties of discretization schemes. The inability of the central differencing method in some convection diffusion problems requires us to study the properties of different discretization schemes. The most important basic properties of discretization schemes can be summarized in 7 categories. 1. Consistency. 2. Conservativeness. 3. Boundedness. 4. Transportiveness. 5. Stability. 6. Order of accuracy. 7. Economy. We will now discuss each of these categories in more detail. Consistency. The discretization schemes are consistent if when the grid size goes to 0, the algebraically discretized equations turn into the continuous governing equations. Conservativeness. To ensure conservation of the variable phi for the entire computational domain, the flux of phi leaving a control volume across a certain phase must be equal to the flux of phi entering the adjacent control volume through the same phase. To achieve this, the flux through a common phase must be represented in a consistent manner by one and the same expression in adjacent control volumes. The gradient of the quantity phi on the surface of a control volume is directly related to the flux of this quantity across that surface. For instance, in this figure, the variable phi changes linearly between the two cell nodes P and E, and thus the gradient of phi is expressed by the same equation on the common surface between these two adjacent control volumes P and E. While in this figure, the gradient of phi is expressed by different equations on the common surface between the two adjacent control volumes P and E. Thus, in this case, the conservativeness is not achieved. Boundedness. In convection diffusion problems without source terms, the solution results are bounded by the maximum and minimum values of the flow variable at adjacent nodes. For example, the value of phi at the node P without the presence of source terms satisfies the following equation. Here, phi I indicates the values of phi in the neighboring nodes. For this purpose, two important conditions must be met. 1. All the coefficients of the discretized equation must be positive, i.e. a and b greater than and equal to 0. Physically, this implies that an increase in the variable phi at one node should result in an increase in the value of the same variable at neighboring nodes. 2. Discretized equations for all nodes form a set of algebraic equations as shown here that must be solved. Iterative methods are commonly used to solve this set of equations. It is shown that for the convergence of the iterative method, the sufficient condition is as follows. If this condition is satisfied, the matrix of coefficients becomes diagonally dominant. To achieve diagonal dominance, we need large values of net coefficient AP minus SP. Therefore, we need to make sure that the source term SP is always negative, which means that minus SP is positive. Consequently, this adds to the value of AP. Transportiveness. The effect of flow direction on the transport of information must be considered in the schemes for the discretization of the convection term. Accordingly, the upstream nodes have a more dominant effect on the value of phi than the downstream ones. The Peclet number, which is defined as the ratio of the convection to diffusion and is defined in this equation, is a good indicative of the measure of the relative strength of convection and diffusion. If Peclet number equals 0, the transport process only includes diffusion, and if Peclet number approaches infinity, the transport process is done only through pure convection. For Peclet equals 0, according to this figure, the diffusion of the variables is done in all directions. Therefore, the values of the variables at E will be affected by the upstream values as well as the downstream values. As the Peclet number increases, the contours change shape from circular to elliptical in the direction of the flow. Therefore, most of the effect will be from node P on the node E. In this case, the values of the variables at P are hardly affected by the values of the variables at E. In the case of pure convection, all the properties at node P will be quickly transported downstream toward E. Therefore, the value of the variable phi at the node E will be only affected by the upstream conditions. Note that it is very important that the relationship between the magnitude of the Peclet number and the directionality of influence known as the transportiveness is considered in the discretization scheme for convection. Stability. The scheme is stable if small errors such as truncation error and round-off error do not grow during the solution process of the resulting system of algebraic equations. Order of accuracy. Accuracy refers to how close a numerical solution is to the exact solution. However, in most cases, the exact solution for the problem to be solved is unknown. Therefore, a direct comparison to check accuracy is not possible. An alternative is to consider the truncation error as a measure of accuracy. Thus, the order of accuracy is related to the size of the truncation error in the discretized representation of a quantity. The order of accuracy can be obtained by expanding the Taylor series over a grid. A higher order of accuracy can be obtained by using more nodes in estimating a quantity. Note that the schemes with high order of accuracy generally have the problem of stability and boundedness. The order of a numerical scheme indicates the rate of error reduction if the grid is refined. Note that the error here refers to the truncation error that results from the expansion of the Taylor series, and the computer's round-off error is neglected. To study the truncation error in the central differencing and Upwind schemes, we are going to use the following one-dimensional uniform structured grid. The order of the discretization schemes used for convection-diffusion problems can be obtained by expanding the Taylor series of node values around the control volume surfaces. For example, for nodes on both sides of the eastern surface E, we can write these relationships. As can be observed in this equation, we have phi E equals phi P plus O delta X. This is exactly the Upwind scheme, and thus it can be concluded that the Upwind scheme is a first order scheme. Adding up these equations and dividing both sides of the resultant equation by 2, we are going to have the following equation. Therefore, it is observed that the central differencing scheme has a second order truncation error. It can be shown that if the order of truncation error in the discretization of the convective term is odd, we are going to face a problem called numerical diffusion or false diffusion, which I will be covering more later on in this video. If the order of truncation error in the discretization of the convective term is even, we are going to face a problem called dispersion, in which the solutions are going to have an oscillatory behavior. Schemes with lower order of accuracy, such as the Upwind scheme, produce considerable numerical diffusion in 2- and 3-dimensional calculations when the velocity vectors are not aligned with the grid lines. Economy. The economy is related to the time required to compute realistic flow problems using a specific scheme, which should not be prohibitively time-consuming. Evaluation of the central differencing and Upwind scheme for convection diffusion problems. Central differencing scheme. Consistency. The central differencing scheme uses consistent relationships to calculate fluxes on control volume surfaces as shown here. Therefore, this scheme has consistency. Boundedness. The coefficients of the discretized convection diffusion equation over this one-dimensional uniform grid are as shown here. Based on the continuity equation, this relationship exists between CE and CW. Thus, for AP, we obtain this equation, which means that the boundedness is satisfied for this coefficient. For the coefficient of the eastern node, AE, this phrase can become negative if the convection is dominant. Therefore, in order for the coefficients to always remain positive, it is necessary that the absolute value of C be smaller than 2D. In other words, the absolute value of Peclet number should be less than 2. If Peclet number is larger than 2, the east coefficient will be negative. This violates one of the requirements for boundedness, which requires that all the coefficients of the discretized equation be positive. Transportiveness. To calculate the diffusion and convection fluxes, the central differencing scheme considers the effect of all adjacent nodes on a mutual phase, as we can see here. Therefore, this scheme is unable to identify the flow direction or the strength of convection relative to diffusion and does not have the property of transportiveness for large Peclet numbers. Accuracy. The central differencing scheme has a truncation error of second order. In order for the scheme to be stable and accurate, it is only necessary to guarantee that the Peclet number is less than 2. The Peclet number, as can be seen here, is a function of fluid properties, gamma and rho. flow velocity u and the size of the grid delta x. Thus, to guarantee that the Peclet number is less than 2 in the whole computational domain, we can either reduce the flow velocity u or reduce the grid size delta x. Due to this limitation, the central differencing scheme is not a suitable method for discretizing equations for general fluid flow calculations. Upwind scheme. Consistency. The equations used to calculate the fluxes on the control volume surfaces as shown here are consistent. Therefore, this scheme has consistency. Boundedness. In this scheme, all the coefficients of the discretized equations as presented here will be positive. Therefore, this scheme satisfies the boundedness criterion. Transportiveness. The upwind scheme is able to identify the flow direction as is shown here, and therefore the information of the upstream nodes of the flow will have more influence on the downstream nodes. Accuracy. Upwind scheme is based on backward differencing formula, and therefore it is only first order on the basis of the Taylor series truncation error as presented here. The main drawback of the upwind scheme is that it produces erroneous results when the flow is not aligned with the grid lines. In these cases, the generated error has a diffusion-like appearance and it is known as false diffusion, which will be addressed later in this video. Steady state two-dimensional convection diffusion equation. In this section, we are going to study the steady state convection diffusion process in two-dimensional mode and discuss the accuracy of the two methods introduced earlier, the central differencing and the upwind schemes. For this purpose, we are going to use the two-dimensional uniform Cartesian grid as shown here in this figure. Uniform grid means that the sizes of the control volumes and the distances between the nodes remain unchanged in the whole computational domain. The steady state transport equation of a quantity phi can be written as shown here, where F, which stands for flux, is defined as follows, where rho is the fluid density and u is the flow velocity vector, which is written as follows in terms of its components. In the finite volume method, this transport equation is integrated over the control volumes as shown here. Using Gauss divergence theorem, this equation can be written as follows. Based on this figure, this equation can be written as shown here, where the areas of the eastern, western, northern, and southern surfaces are defined as follows. The same as before, the fluxes in this equation consist of convection and diffusion processes. For example, the phrase dot product of the flux and area vector at the eastern surface signifies the total flux passing through the eastern surface of the control volumes, which can be written as follows. In this equation, the convection term can be rearranged as shown here. Using the upwind scheme, the standard discretized equation for the two-dimensional case is expressed as shown here. Solving a steady state two-dimensional convection diffusion problem. Consider the convection of the scalar quantity phi in the squared domain as shown here in this figure. The boundary conditions on the surface of the control volume is shown in this figure. Along the southern and eastern boundaries, the phi is assumed to be 1, whereas along the northern and western boundaries, it is equal to 0. The flow field in the domain is assumed to be uniform as shown here. Therefore, the velocity vector will be along the diameter shown in this figure. Using the two schemes, the central differencing and the upwind, the distribution of phi is calculated in this computational domain for the case where the Peclet number approaches infinity and the results are compared against the exact solutions. In other words, there is no diffusion in this domain. Gamma equals 0. In the absence of the diffusion process over the upper part of the square above the diameter, phi will be equal to 0 everywhere, while over the lower part of the square below the diameter, phi will be equal to 1 everywhere. In the presence of the diffusion, a diffusion-like layer will be created around the diameter where the values of phi will be between 0 and 1. The distribution of phi along the center line of the square, as is shown in this figure, is plotted here in this figure and compared with the exact solution. As can be inferred from this figure, the Upwind scheme presents the distribution of phi in such a manner that it implies that there is a diffusion-like layer even in the absence of the diffusion process. In other words, the profile generated by the Upwind scheme is smeared and highly inaccurate but very smooth. Additionally, it is observed that the central differencing scheme gives an oscillatory distribution of phi which does not exist in the exact solution. Note that due to the infinite value of the Peclet number, the oscillations created by the central differencing scheme cannot be eliminated by refining the grid. False diffusion and numerical dispersion in numerical solutions. This section examines in detail the behavior of the central differencing and Upwind schemes, which are the basis of other advanced methods. One of the main disadvantages of the Upwind method, which has a first order of accuracy, is its high diffusive performance. To clarify the reason for this, consider the two-dimensional equation of convection without the presence of a diffusion process and source term as shown here. For simplicity, a constant flow field with U and V greater than 0 is assumed. Here, U and V are the Cartesian velocity components in x and y directions respectively, and the density is assumed to be constant. After integrating this equation, the values of phi on the control volume surfaces are estimated by the Upwind schemes as presented here. Considering the computational domain shown in this figure, phi s and phi w are expanded around phi p by the Taylor series as shown here. The above equations can be rearranged and rewritten as follows. These equations are now substituted into this equation, and consequently we're going to have the following equation. By assuming that delta x equals delta y, u equals y, this equation is simplified into this one. This differential equation that we just obtained is known as the equivalent differential equation. The left-hand side of the equation resembles the original differential equation as is shown here, while the right-hand side indicates the truncation error. A comparison of this equation with the convection-diffusion equation shows that the first term on the right-hand side of this equation is equivalent to the diffusion term. Thus, it can be seen that although the problem in question is a pure convection problem, using the Upwind scheme, the solution obtained implies as if a diffusion process is present in the problem. This phenomenon is called the false diffusion, which is also called numerical viscosity in momentum equations. The false diffusion coefficient in the Upwind scheme is proportional to the size of the grid delta x. Therefore, by refining the grid, its effect is also reduced, but it never disappears. Now let's solve the two-dimensional pure convection problem using the central differencing scheme as presented here. Using the same computational domain, phi e and phi w are expanded around phi p by the Taylor series as shown here. Subtracting these two equations from each other and dividing the both sides of the resultant equation by 2 delta x yields this equation. Applying the same procedure for y direction, we are going to have this equation. By assuming that delta x equals delta y, u equals v, and substituting these equations into this one, we're going to have the following equation. The problem in question was a pure convection problem, but in the resulting equivalent equation, which is solved by the central differencing scheme, a term of the third derivative appears on the right hand side as is highlighted here. This term is responsible for creating the numerical dispersion, which causes the solutions to have an oscillating behavior. Therefore, the discussion in this section can be summarized as follows. The Upwind scheme produces false diffusion and causes the gradients to become smeared. The central differencing scheme causes oscillations in the solutions. Advanced schemes for convection discretization. Through understanding the properties of the discretization schemes described in the previous sections, more advanced schemes for the discretization of the convection term are now presented. First-order schemes. A few first-order schemes that are used to discretize the convection-diffusion equations have been proposed, some of which are still used. Here, two schemes of this type are presented. power law scheme. This method covers the convection and diffusion terms together and does not treat them separately. The power law scheme uses the assumption of a local profile, which is an estimate of the exact solution of the local convection diffusion equation. In multidimensional problems, the behavior of this scheme is the same as the Upwind scheme. The use of this scheme is not recommended for the reasons that will be presented later in this video. The one-dimensional steady-state convection diffusion equation is written as follows. By integrating this equation over the control volume P as shown here in this figure, we will have this equation. The assumption of the one-dimensionality of the problem yields this equation. The surface areas are equal to 1, which means that the fluxes on the eastern and western control volume surfaces can be written as follows. To estimate the values of phi together with the values of its gradients on the eastern and western control volume surfaces, the scalar variable phi needs to be expressed as a function of x. In the absence of a source term, the total flux on a control volume surface remains unchanged as shown here. The exact solution of this equation using the values of phi at P and E, phi P and phi E at two adjacent nodes is expressed as follows. Therefore, the flux through the eastern surface E of the control volume is expressed as shown here, where CE is defined here. Using the same procedure, an equation for the western surface W can also be obtained. Therefore, the standard discretized equation using the power law scheme is expressed as follows. Evaluation of the power law scheme. Considering the properties of the discretized equations and the necessary conditions for a stable solution, the evaluation of this scheme can be summarized as follows. 1. The conservation of fluxes is satisfied on the control volume surfaces. 2. As can be inferred from the flux expression over the eastern control volume surface, for large values of Peclet number, this equation turns into this equation. Therefore, the flux depends only on the upstream node. In other words, the scheme is able to account for the flow direction. 3. The power law scheme also satisfies the boundedness criterion, as all the coefficients in the discretized governing equations are positive, as are presented here. This scheme provides an accurate solution for one-dimensional steady-state convection diffusion problems without the presence of the source term, as well as at a constant velocity field u and coefficient gamma, irrespective of the Peclet number and the size of the grid. The power law scheme has not become popular for the following reasons. 1. The scheme is not accurate for variable velocity field u and coefficient gamma, and also in the presence of the source term or in 2 and 3-dimensional flow problems. 2. Calculating exponential terms are very time consuming. Hybrid scheme. The hybrid scheme is a combination of the central differencing and the Upwind schemes. The hybrid scheme takes advantage of the strength of these two schemes. This scheme employs the central differencing scheme, which is second order accurate for Peclet numbers less than 2, while it uses the Upwind scheme for Peclet number greater than 2, which is first order accurate but takes into account the effects of the flow direction. For example, for u greater than 0, the coefficients of the discretized momentum equations are as follows for Peclet number less than and equals to 2 and for Peclet number larger than 2. It can be easily seen that for low Peclet numbers, this is equivalent to using central differencing for the convection and diffusion terms, but when the values of Peclet number are larger than 2, it is equivalent to using the Upwind scheme for convection and setting the diffusion to 0. The general form of the discretized equation using the hybrid scheme for one-dimensional steady-state problems is as follows. Evaluation of the hybrid scheme. This scheme respects the conservation of fluxes on the control volume surfaces. Additionally, all the coefficients of the discretized equation are positive and take into account the effects of the flow direction. This method is very stable and it is first order accurate. The hybrid method was very popular at the time of its presentation and was widely used due to its stability. However, at present, in most applications, the flows that are being studied operate at high convection and low diffusion regimes, with Peclet number rarely being less than 2. Therefore, the hybrid scheme in most parts of the computational domain becomes the Upwind scheme with first order accuracy. For this reason, researchers are more inclined towards developing more accurate schemes with higher order of accuracy. So far, we observed that both the central differencing and Upwind schemes have their limitations, which makes them unsuitable for the discretization of the convection term. As you may remember, the central differencing scheme creates oscillations in the solutions, while the Upwind scheme creates false diffusion in the solutions. However, as the Upwind scheme has the ability to consider the flow direction, efforts were made to improve the accuracy of this scheme by interpolation with higher accuracy. In the Upwind scheme, to obtain the value of the variable phi on the eastern surface of the control volume E, it was assumed that this variable has a uniform distribution. In other words, for CE larger than 0, phi E equals phi P. Instead of a uniform profile assumption, a higher order profile assumption, such as a linear or quadratic profile, can be used for phi. For CE greater than 0, the variable phi, by using the Taylor series expansion around the node P, can be written as shown here. Second order Upwind scheme. The second order Upwind scheme can be obtained by assuming that phi varies in a linear fashion. Therefore, based on this figure and using the first two terms on the right hand side of the Taylor series expansion as shown here, we're gonna have this equation for phi E. The second order Upwind scheme has a truncation error of second order. To obtain the value of phi at the eastern surface, we need to calculate the value of the gradient of phi at this surface. This gradient can be calculated using either a central difference or backward differencing or forward differencing. Using the central differencing, this gradient is estimated as shown here. Therefore, the value of phi at the eastern surface can be written as shown here. By adding and subtracting phi p divided by 4 to this equation, we're going to have this equation. This is the second order Upwind scheme. However, we can reach a somewhat different result by using a backward differencing scheme for the discretization of the gradient of phi at the eastern face as shown here. In this case, the value of phi at the eastern surface is written as follows. This is another version of the second order Upwind scheme. Now let's evaluate briefly these second order Upwind schemes. 1. These schemes are second order accurate. 2. The second order Upwind schemes presented here are not bounded and they can create negative coefficients in the standard form of the discretized equation. Third order Upwind scheme, quick. By keeping the second order derivative of phi in the Taylor series expansion, the third order Upwind scheme can be obtained as shown here. The first order and second order derivatives in this equation can be calculated as presented here using the nodal values of phi. Note that the second order derivative is approximated as shown here. Therefore, the value of phi at the eastern face can be approximated as follows. This equation can be rearranged as follows. This is the third order Upwind scheme, which is also known as the quick scheme. Quick stands for quadratic Upwind interpolation for convective kinetics. Note that again, it is possible to have negative coefficients in the discretized equation, which results in oscillations in the solutions. Of course, the resulting oscillations in the solutions are much smaller than those observed using the central differencing method. As can be inferred from this equation, in the quick scheme, the value of the variable phi on the surface of the control volume is calculated by a quadratic function that passes through 3 nodes, 2 nodes upstream and 1 node downstream. These figures show the position of the eastern surface depending on the direction of flow. For instance, based on this uniform one-dimensional grid, the values of phi at the western and eastern surfaces of the control volume P for C greater than 0 can be written as shown here. Therefore, the discretized equation in a standard form and its coefficients using the quick scheme is written as follows. The same equations can be obtained for C less than 0 based on the quick scheme. For a flow field in which a fluid can flow in different directions, a general relation can be written as follows, where alpha is defined as shown here. Evaluation of the quick scheme. The quick scheme has a higher order of accuracy than the first order Upwind and central differencing schemes, and at the same time it has the characteristics of the Upwind scheme. In summary, the quick scheme has the following characteristics. It is third order accurate, the conservation of fluxes on the volume control surfaces is satisfied. It considers the effect of flow direction. However, it is not bounded. Therefore, in this scheme, there is no guarantee that the coefficients of the discretized equations, as highlighted here, will always remain positive, which can lead to instability in the solutions. In order to eliminate this weakness, the quick scheme has been reformulated in many ways, where all of the negative coefficients in the discretized equations are moved into the source term. Discretization of the convective term over non-orthogonal unstructured grid. Over unstructured grids where the cell face is not orthogonal to the line connecting the cell centroids as shown here in this figure, the schemes used for the discretization of the convective term are reformulated in terms of gradients of phi values at cell faces and nodes. For instance, the central differencing scheme over a non-orthogonal unstructured grid is written as shown here, where RE is the position vector of the cell face E with respect to the coordinate system, and RP is defined here in this figure. To check if this equation is correct, let's assume that the grid is uniform as shown here. Thus, this equation can be simplified into this equation, which is exactly the same equation that we obtained for the estimation of the cell face value of phi in terms of nodal values at P and E using the central differencing scheme over a uniform grid. Similar formulations can be encountered, for instance, in the user guide of commercial or free CFD codes for other schemes presented earlier in terms of gradients of phi values at cell faces and nodes. Flux-limiter schemes. So far, in all the schemes presented, it is observed that the matrix of coefficients is constant. In other words, these coefficients are independent of the solution variable phi. It is demonstrated that the only scheme of this type that is unconditionally bounded is the first order Upwind scheme, which is first order accurate. For schemes such as the quick schemes, the values of phi calculated at the volume control surfaces can be outside the range of the values of phi in the neighboring nodes. In other words, in these high order schemes, the boundedness is not satisfied. To solve this problem, modern schemes have been developed which use solution-dependent limiters that ensure both the boundedness of the solutions and the high order of accuracy. For schemes which are based on the values of phi over 3 nodes, if phi UU is less than phi U is less than phi D, or phi UU is greater than phi U is greater than phi D, then it can be said that the phi is uniformly increasing or decreasing as shown here. Here in this figure, we can see the fluid flow direction, and D stands for downstream, U upstream, and UU upstream upstream. A necessary condition for high order schemes to be bounded is that they automatically turn into the first order Upwind scheme whenever the increase or decrease in phi is non-uniform as shown here. Two popular schemes based on this idea, which are also referred to as the Flux-limiter schemes, are presented here. Van Leer scheme. This scheme is second order accurate except for the maximum and minimum local points where the increase or decrease in phi is non-uniform, which is first order accurate. A clear advantage of this scheme is its boundedness. If this condition exists, then the face value of phi is equal to the value of phi at upstream node. In other words, the first order Upwind estimation is used. Otherwise, the face value of phi f is estimated using this equation. In summary, this scheme can be written as follows for uniform variation of phi, and for non-uniform variation of phi where the first order Upwind scheme is used. In evaluating this scheme, it can be said that it is a second order accurate over the whole computational domain except for the minimum and maximum local points where it is first order accurate. This scheme is generally known as a second order scheme, and also it is completely bounded. UMIST. In summary, this scheme can be written as follows for uniform variation of phi and for non-uniform variation of phi where the face value of phi is equal to the value of phi at upstream node. In other words, again, the first order Upwind estimation is used for non-uniform variation of phi. R is defined here. The summary of the evaluation of this scheme is as follows. In the whole computational domain, it is a third order accurate scheme except in the minimum and maximum points where it is first order. In general, this scheme is considered a third order scheme, and also it is completely bounded. High resolution schemes. The high resolution schemes are developed through a combination of high order schemes and a convection boundedness criterion, which ensures that no oscillatory behavior is experienced in the solution. Convection boundedness criterion are developed using the normalized variable diagram introduced by Leonard 1979. The normalized variable diagram is a plot which describes the locally normalized convected control volume phase variable phi f with respect to the normalized adjacent upstream node variable. To explain further, consider the variation of a convected scalar variable phi x, y, z along a direction normal to a control volume phase f as shown in this figure. Here, D stands for downstream, C is central, U upstream, and F phase. Note that the labeling of node values downstream, central, and upstream depends on the normal velocity direction, as of course does the choice of node for phi u, the value of the variable phi at upstream node phi u. The locally normalized variable phi is defined as follows: phi tilde equals phi minus phi u divided by phi d minus phi u. With this normalization, this relation turns into this equation, since the normalized values of phi d and phi u become equal to 1 and 0 respectively as shown here. The normalized value of phi at c, phi tilde c, is used as an indicator to identify if the field phi is uniform or non-uniform. For instance, for the values of normalized phi at c, phi tilde c, between 0 and 1, the variable phi changes monotonically, i.e. increases or decreases uniformly, as shown here in these figures. Additionally, as shown here, for the values of normalized phi c, phi tilde c larger than 1 and less than 0, there is an extremum at c, as shown here schematically in these figures. Finally, the values of normalized phi at c, phi tilde c, equal to 0 and 1 indicate a gradient jump, as shown here in these figures. Using the normalization, the functional relationships of high-order upwind schemes presented previously are reduced into linear relationships between the normalized phi value at phase f, phi tilde f, and the normalized phi value at node c, phi tilde c. For example, the normalized functional relationships of the high-order schemes are as follows: central differencing upwind scheme, second-order upwind scheme, third-order upwind scheme. The normalized phase values phi tilde f obtained from these schemes are shown in this plot as a function of normalized adjacent upstream node value phi tilde c. This plot, in fact, is the so-called normalized variable diagram. Based on the normalized variable diagram, except for the first order upwind scheme, all the second order and third order schemes pass through the point Q, 0.5, 0.75. The high order schemes shown in this figure drastically decrease the truncation error suffered by the first order upwind scheme. However, one of the main shortcomings of these schemes is their unboundedness, i.e. their tendency to produce undershoots and overshoots and even oscillations. Therefore, work on developing high-order oscillation-free convection schemes resulted in several techniques such as the Flux-limiter schemes presented earlier. In these schemes, a composite procedure where high-order schemes are combined with bounded low-order ones, with the switch between them being controlled by a certain criterion. These composite schemes can be explained within the framework of the normalized variable diagram. Based on the normalized variable diagram, it can be demonstrated that for a convection scheme to have the boundedness property, its functional relationship should be continuous, should be bounded from below by the normalized phi value at c, phi tilde c, and from above by unity, and should pass through the points 0, 0 and 1, 1. Should pass through the upper triangular in the monotonic range for the values of normalized phi at node c between 0 and 1, phi tilde c between 0 and 1, and for the values of normalized phi at c, phi tilde c larger than 1 and less than 0, the functional relationship for the convection scheme should be equal to the normalized phi value at node C, phi tilde C. Mathematically, these conditions can be written as shown here in the context of the normalized variable diagram. Thus, again, for the convection scheme to have the boundedness property, its functional relationship should be continuous, should be bounded from below by the normalized phi value at C and from above by unity, and should pass through the points 0, 0 and 1, 1, should pass through the upper triangular in the monotonic range, i.e. for the values of normalized phi at node C between 0 and 1, and for the values of normalized phi C, phi tilde C, greater than 1 and less than 0, the functional relationship should be equal to the normalized phi value at node C, phi tilde C. This criterion is shown in this figure. Thus, to construct a high resolution scheme for the convection term which possesses the boundedness property, the monotonic profile in the range of the values of normalized phi at C, phi tilde C between 0 and 1 should pass through the points 0, 0 and 1, 1 while remaining within the upper triangular shaded region on the normalized variable diagram. Additionally, in the non-monotonic range, i.e. for the values of normalized phi C, phi tilde C, larger than 1 and less than 0, the profile should follow the first order upwind profile. A number of well-known high-resolution schemes have been developed in this manner, such as SMART and MUSCL, which can be found in the literature. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.